In this video, we're going to talk about the difference between endothermic and exothermic reactions. First, let's talk about what we mean by thermochemistry. This is kind of the fun part of chemistry, the studying of energy released or absorbed by chemical reactions. There's a lot of different kinds of energy. The easiest to measure and to manipulate and to think about is probably heat. And so we're going to focus on heat transfers. But somewhere in the back of your mind, keep in mind that light and sound are also forms of energy that chemical reactions give off or absorb. The ultimate source of any amount of energy released in a chemical reaction are the bonds. The bonds stored The bonds in a chemical compound store an enormous amount of energy, and we call that chemical potential energy. When you break a bond, it always requires an input of energy. Whether we're talking reactants or products, breaking bonds always requires an input. And the forming of a bond always releases energy. The question is, does the sum total amount of energy that you need to input to break bonds outweigh the sum total amount of energy that you get by forming new bonds? So it takes energy to break the bonds of reactants, but when you form the bonds of the products, is that greater or less than the sum total of the energy that you put in to breaking reactant bonds? Let's talk about the two kinds of reactions. Endothermic. Endo. That's a root word that means within. So like an endoskeleton is a skeleton within your body. The opposite, an exoskeleton, like a lobster or a crab, that's a skeleton outside the body. So remember those roots. Endo means within. You're taking energy in. The energy released by forming product bonds is less than the energy consumed in breaking reactant bonds. In order for an endothermic reaction to occur, heat has to be supplied to the reacting molecules from the surroundings. Think of melting ice. If you have some ice cubes and we're going to transition from the solid state to the liquid state, it's sucking in heat energy. It's part of the reason why having ice in your drink makes it fun or better to drink, is because it cools it down. It's sucking heat energy away from the other liquid in the drink that you're having. If you include the word heat in a chemical equation, which I'm going to encourage you to do this unit, it would look something like this. Heat plus solid water yields liquid water. Endothermic reactions, as you can imagine, feel cold to the touch. So imagine a nice cold glass of iced tea on a hot summer day. Well, that's going to feel cold to your hand. That's because it's endothermic. Just the opposite is going to be the case for exothermic reactions. Exothermic reactions release heat to the surroundings. If we compare the energy released by forming product bonds to the energy consumed in breaking reactant bonds, we would say the energy released by forming product bonds is greater than that consumed in breaking reactant bonds. Exothermic reactions give off heat. They're transferring thermal energy from the system to the surroundings, and ultimately the source of that thermal energy are the chemical bonds that make up the substance. So for a nice example, think of a campfire. Now, the chemical formula for wood is actually pretty complicated and highly variable. Different wood would have different formulas. But if we put it kind of crudely and just say logs yields the ashes, which is what is left of the log after the reaction, plus carbon dioxide, plus a good amount of heat energy, we have a rough equation for burning wood. If you've ever sat around a campfire, you know that exothermic reactions are hot to the touch. So they're giving off tremendous amounts of heat energy. Okay, let's do some more side-by-side comparisons. We're working on the qualitative level right now, and we'll get quantitative later in this unit. Endothermic reactions take in or absorb heat energy as they proceed. The surroundings of the reaction, as a result of that taking in of heat energy, get colder. And this is important, the reactants are lower in chemical potential energy than products. In other words, to get from that cold energy, the lower energy state to the higher energy state, it needs to take in heat energy from the surroundings, and that's why the reaction feels cold when you touch it. If you were writing a chemical equation and using heat energy as if it were a chemical, it would look like this. Reactants plus heat energy yields products. So the heat goes on the left side of the equation. Let's contrast that with exothermic reactions. We'll see just the opposite trends for exothermics. They give off heat energy as they proceed. The surroundings get hotter, not colder. Reactants are higher in chemical potential energy than products. And if we were to write a chemical equation with heat as part of it, we would put heat on the right side of the equation. Reactants yields products plus heat. As you can imagine, we love graphing in chemistry. There's a way to represent this. This is called an energy curve. On the y-axis is stored chemical energy, specifically chemical potential energy, the energy of the bonds. On the x-axis, they're not labeling it, but sometimes we write reaction progress, meaning as you're progressing from reactants to products. Reactants start on the left side of the equation and products on the right side. The reason we don't say time is, as we know from equilibrium, you don't always end up with 100% products as time goes on. So in the case of an endothermic reaction, the reactants are low down in chemical potential energy and the products are higher up. And as the reaction progresses, you need to climb up an energy hill. That's the amount of energy absorbed from the surroundings. In an exothermic reaction, we see just the opposite trend. Again, we have stored chemical energy or chemical potential energy on the y-axis and reaction progress that's not labeled here on the x. But the reactants start out high in chemical potential energy and the products are low. As we move from left to right, we're going down an energy hill, which means that we'll be releasing energy. The surroundings will get hotter as a result. And the amount of energy released is equal to the difference in the chemical potential energy levels between the reactants and the products. Now, if you Google energy curve, you'll see slightly more complicated graphs that include activation energy. I'm glossing over that right now deliberately. I just want you to focus on the simple difference between energy absorbed and energy released. Okay, one last thing, and this is going to set us up for the calculation of energy. We measure energy with the SI unit called the joule, and a joule is a kilogram meter per second squared, or meter squared per second squared, which is really a Newton times a meter. A Newton is a kilogram meter per second, and if you times that by another meter, you get the joule. In a deep way, work is the same thing as energy, and we know that work is force times distance. So the background from physics is that if you move something across a distance, if you apply a force across a distance, that's either work or energy. Work is merely the manifestation of energy. In everyday life, to give you a sense of this, a joule of energy is the amount required to lift a small apple 1 meter straight up. It's also the amount of energy to heat 1 gram of dry, cool air by 1 degree Celsius. So the joule is the more commonly used unit, but I do want you to be familiar with the other unit that's also used to measure energy. It's the calorie. This is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. And it turns out the amount of energy required to do that, stated in joules, is 4.18 joules. We're going to tie this eventually in a really cool lab that we do to nutritional calories. So the calorie that we're talking about here is actually 1/1000th of a nutritional calorie. All right, good work, students.